Okay, so hello. Um, we had a snowstorm, so this is to make up for it. So, of course, this is Physics 2111, lecture number one. We're going to cover chapters 1 through 2.3. Uh, so, initially, we're really, for the first test, we're going to be doing chapter 1 through chapter 5, and then there's this little section 6.2 for the first test, but um, it's kind of I wouldn't say it's a whirlwind. The chapters are they're not super dense, and anyway, this will get us back on track. If I can do this bit right here, we should be okay. Maybe I'll do a little more. I don't know. It depends on how far we get here today. So, anyway, that's our goal, to get back on track for this missed weather day. And what we want to talk about is the scope and scale of physics. This is section 1.1. We're going to just start right there at the beginning. Now, I think, of course, every single time, these things really should be read. Okay, so in the book, read them. You'll find that everything I'm saying is basically straight out of the book, and don't let that bore you. I'm trying to make it as entertaining as possible, yet still learning. You're hopefully still learning from that entertainment. Let's see how entertaining I am. But read the book, okay? And then you can go, oh man, he's just saying the same thing the book says. Well, yeah, that's true, but some people like to read and get that information. Some people like to hear it verbally and get that information. Some people would rather see videos and get it that way, and that's fine too. And sometimes videos will help, and periodically we'll be doing videos. It's going to be an unavoidable thing for us. Okay, so let's get going. The scope and scale of the universe. All right, well, first of all, it's universal. Okay, so universal meaning from the extremely small, the smallest things you can possibly imagine, all the way up to the biggest things, okay? And then fractal. So it's small and fractal. Okay, now the fractal part is my addition, I think. I can't remember, actually. Haven't read the book in a while, but I believe the book doesn't talk about the fractal nature of the universe. However, it is. And at all scales, at all levels, we have things that ball up. So it could be a galaxy, or it could be a subatomic particle. Okay? And these things have balled up. Okay? And they come from movements of flow of energy. Okay? So flow of energy is where all that comes from. Okay, so galaxy, even larger structures than galaxies, by the way. So, I missed an R in my universal. Okay, so all right. So what are the scales? All right, what is this scale? This universal scale? What does that mean? Well, we're going from. This is where I would be asking you guys, what is the smallest thing? Okay, and hopefully you will be able to come up with the Planck length. This is the smallest length that we can possibly have for anything. It's weird. This is a ramification of quantum physics, actually. Quantum physics. So they didn't know this before quantum physics, that this Planck length was the thing that we couldn't really get smaller than. But we know now, and thanks to this fellow Planck, Planck, however you want to say it. As an ignorant American, I say Planck. So 10 to the minus 35 meters. Okay, now do you guys remember in class we were talking about the size of a door, or my height, or someone's height roughly about 6 feet tall? They are approximately 2 meters tall. Okay, so cut that person in half. You've got 1 meter from there to there. And if you cut them in half, there's probably some blood over there. I'm just kidding. Okay. So we've got this 2 meter or 1 meter from one side to the other, and then you start to divide it up, right? So we've got decameters, decameters or decimeter. That's 10 centimeters. So if you divide it by 100, you've got centimeters, and that would be something really small there, right? That's our centimeter. And then you can go into millimeters and all of those other things. A millimeter, so a centimeter is 10 to the minus 2 meters. A millimeter is 10 to the minus 3 meters, and so on. Well, to get to the Planck length, you've got to go 10 to the minus 35 meters, okay? Extremely, really small, all right? And so the Planck length is, just tiny, all right? But it's not unlimited, the amount of tininess we can get to in the world. And we're not going to go into the arguments of why this is true. It's just the way it is, okay? We're just going to assume that some quantum physicist is correct, or a whole bunch of them, which it turns out there are a whole bunch of them, and they all agree. So 10 to the minus 35. Okay, now, how big can it get, right? How big? So as far as we know, there are some cases where lately people are starting to think things are a little bit different than what I'm about to tell you in the research currently, but don't worry about that. We're going to just stick with what we have in the book. So we've got 3.8 billion. So a billion, I could write billion, or I'm going to write times 10 to the 9 light years. So there's a light year in length. Okay, so what is a light year? It's the distance. If you were to allow light to travel for 1 year at the speed of light in a vacuum, it would go 1 light year distance. Okay, well, that's a lot. It's pretty far, right? How far is that? In meters, that's 1.38 times 10 to the 10. Wait. I'm sorry. I don't know why I wrote that other number. I'm probably trying to make a point about something. Let's do this. 1 light year is equal to 9.5 times 10 to the, what is that, 15 meters. Okay, so 9.5 times 10 to the 15 meters. So not 2 meters, not 2 meters, but 9.5 times 10 to the 15 meters. Okay, so let's do a little a kilometer is 10 to the 3 meters. A megameter is 10 to the 6 meters, and a gigameter is 10 to the 9 meters. So we've got 10 to the 15 meters. We can go up to 10 to the 15 with these words, but it's pretty big. Okay, so let's just leave it at that. So what is our range? What is our range? Before we do that, let's do. So we've got 1.38 times 10 to the 9 light years. How many meters is that? So 3.8 times 10 to the 9 light years. For us, we can take this conversion and do our thing. So we want to multiply by 1, okay, to get how many we're looking for. I'm going to put it in blue here. We're looking for this converted to meters, okay? And we're going to use this conversion, okay? Well, what does it mean? If this 1 light year is equal to 9.5 times 10 to the 15 meters, then that means if we were to divide 1 light year by 9.5 times 10 to the 15 meters, that would give us 1. So we could say 9.5 times 10 to the 15 meters divided by 1 light year equals 1. Well, anytime you multiply anything by 1, you're not changing it, right? So we can multiply our 13.8 times 10 to the 9 light years. We're going to multiply that by 9.5 times 10 to the 15 meters and per light year. And that's going to give us, we can cross out light years at this point, and it's going to give us our answer in meters. And it turns out that that's 1.31 times 10 to the 26 meters. So that's how large, as far as we know at this point, our best guess of how large the universe is in meters. Okay, so we go from a Planck length scale of 10 to the minus 35 meters all the way up to a universal scale of 1.31 times 10 to the 26. That is a large range of scale that we could possibly have. So what is that range? 10 to the minus 43. I'm going to disregard all the stuff out front, okay? We're just going to disregard that and look at just the exponents. But we get an exponential range of... I did it again. I'm looking at the wrong number again. Sorry. Let's do the math. Okay, so where are we at? We've got minus 35. We've got minus 35. And we've got 10 to the 26. So positive 26. So we want to know how many orders of magnitude are we getting when we do this. Okay, so what's the total order of magnitude? Well, to get that, we have to add those together. So we're going to do it, 26 plus 35. We're going to add them together. We got 1, carry the 1. That'll give us 6. So we have 61 orders of magnitude. So 10 to the 61 orders of magnitude. There's two different ways to think about this. 10 to the 61 is not the orders of magnitude. The orders of magnitude is 61 orders of magnitude, okay? Which means each order of magnitude is a factor of 10, okay? So 10 is one order of magnitude. Magnitude, okay? So we can multiply that Planck length by 10 61 times to get our universal size, okay? And the universe keeps expanding, so it's only getting bigger and bigger and bigger. Things can't get any smaller than the Planck length, but the universe does definitely get bigger. So, yeah. Anyway, right now, at this point in our lives, at what we think we can do 61 orders of magnitude larger than the Planck length for the entire range. Okay, so I hope that is somewhat clear to you. Let's look at time. So we'll make time blue. So let's look at time. And so, of course, the quantum guys, they got together and over all the years, and they came to a conclusion. Planck actually said, hey, you know what? There's a minimum Planck time as well. And that minimum Planck time is 10 to the minus 43 seconds. Okay? I'll write out seconds, but seconds is S, right? We use S for seconds. So we can go all the way from there, but because the amount of time that has happened, that has passed since the origin of the universe, is still 1.38 times 10 to the 10 years. So it's 13.8 billion years. That is a long time, okay? And we can do some conversions there as well to convert our from seconds to years. It's not as easy to convert seconds to years. Maybe we should do it. I didn't do it in my notes, so we'll just do it right now. Okay, so we want to convert seconds to years. Okay, how do we do that? So here's where I'm going to do a few things. First of all, 1 year has how many days in it? Let's do 365 days. So we want 1 year on the bottom. We want 365 days on top. Put a little D for days. We're going to multiply that by how many hours in a day? Okay, well, we've got 24 hours. And I need to have days on the bottom. And since each one of these is just one, you could flip it. You could have it inverted if you want. But we really just want day, right? So we want day in the bottom so that we can start canceling out these things, right? And now we're going to do hours. And since there are 3,600 seconds in an hour, 60 times 60 is 3,600. So 1 hour, I want 1 hour in the bottom, has 3,600 seconds in the top. That cancels our hours. And the next thing you know, we're left with how many seconds since the Big Bang have occurred. Okay, so we're going to get that number here in a second. All right, I think you guys should do it on your calculators just to make sure. I would have you do that in class. 1.38, okay? We're going to take that and we're going to multiply 365 times that. We're going to multiply 24 times that and 3,600 times that. Okay, so that's huge. That's a huge number. And I didn't multiply in this part yet, okay? Because what I really want is to say 4.35 times 10 to the 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7 times 10 to the 7. But all that is also multiplied by this times 10 to the 10. Okay? So that's how many seconds since the Big Bang have occurred. And that makes it easy for us to just write 4.35 times 10 to the 17. Okay, seconds. So we've got 4.35 times 10 to the 17 seconds since the Big Bang. And of course, it's continuing every day. It adds another 24 times 3,600 seconds. But that's roughly where we're at. Okay, so we go from 10 to the minus 43 seconds up to 4.35 times 10 to the 17 seconds. So what does that span? So we've got, how many orders of magnitude is that? That's minus 43 all the way up to 10 to the 17. So we got to add those two things together. I'm sorry. I wrote 10 to the 17. What I really wanted was 17 as the order of magnitude. So we add 17 to 43, and we get our 10 here. We left with 60. So we have 60 orders of magnitude for time. And again, that is a lot, right? 10 to the 60 is a lot. So, good. Okay, so let's lay down orders of magnitude a little bit more. Okay, so orders of magnitude. You know what? I think I've killed orders of magnitude pretty well. I think we've done it. Okay, but what I'd like to do is ask you guys a question about orders of magnitude. And my question is, how many, that's an M, by the way, how many orders of magnitude is 1 year larger than 1 hour? Okay, so how many orders of magnitude is 1 year larger than 1 hour? So 1 hour multiplied by how many orders of magnitude will get us to 1 year? That's the question, okay? All right, so pause, see if you can figure that out. And when you come back, we will solve that. So let's do one. How many seconds in 1 year? We kind of already did that before. We've got 3.15 times 10 to the 7 seconds in 1 year. And so we did that when we did this work right here. Okay, so we started with 1 year, 365 days, 24 hours, 3,600 seconds per hour. But we don't really care about the seconds. We just want the hours compared to a year. How many orders of magnitude is that? So let's come down here and do just the ones that we want. So we've got 1 year. We're going to multiply 1 year by 365 days per 1 year. And that's going to allow us to cancel out our year. We're going to then say, oh yeah, in 1 day I've got 24 hours. So we can cancel out our day, and that should give us 1 hour compared to 1 year. Okay, so we'll do it. We'll multiply our 24 hours by 365. 365, enter 24 times. That's 8,760, which we could write as 8.76, 3 significant figures, times 10 to the 3. Okay. Now, there's a couple other ways to do this, because this makes it times 10 to the 3. So we would say 3 orders of magnitude. However, this is almost 1 order of magnitude, right? 8.76 is very close to 10. So that 10 times 10 to the 3 would be 10 to the 4. So a person might say 4 orders of magnitude. And okay, so what's another way we could have done this? We've got 3.15 seconds in 1 year, and 1 hour. We already came to the conclusion that 1 hour is 3,600 seconds. So let's do that comparison. Let's go back down and do that comparison. So here we have our 3.15 seconds in 1 year. We've got an hour is 3.6 times 10 to the 3 seconds. So if we were to compare these two things with each other, we'd notice that the order of magnitude, we've got 7 minus 3 orders of magnitude, which would give us 4. So here's the 7, here's the 3. Those are our orders of magnitude. 7 minus 3 gives us 4 orders of magnitude. So that's a neat, clear way to see the orders of magnitude. Difference between 1 year and 1 hour. We have shown it 2 different ways. What did we do? Both times we took this number and we said that it is roughly equal. Okay? So the mantissa, they call this the mantissa. We said that the mantissa, not the exponent, was roughly equivalent. Okay, the 2 mantissas. Well, and that's true, right? 3.6 is it's almost 3.15. It's in physics world. Don't get me wrong. You might get that wrong on a problem or a test if you didn't have those two exactly right. But within orders of magnitude, they are definitely close. So we've shown that 4 orders of magnitude is the right answer here. Okay. So, good. Now, our scope of the class. Let's talk a little bit about the scope. And before we continue, I want to set timer for 25 minutes to make sure that we don't go over too far. And if I have to, I'll record 2 of these. So what are we doing? I already said in class we're looking at the 1600s to the 1800s. The scientific work done in these times, and we're certainly not going to go further. It's all got to be less than 1905, because in 1905 we had, they call it the Annulus Miraculabilis or something like that. The miracle year. Einstein wrote 4 papers in that year, and it all led to a changing of the way we look at the world. So, but like I said, Einstein's theories had to include all of the things that were done in this time. So all of those things still occur in our world, and we live in that same world, right? We live in that world. And they did a good job, those old scientists. They did a good job. So we can continue to use those things. Our everyday experiences are on the 2-meter scale. Okay? So, and that's definitely a question on the test. So you want to know about that. And I talked about it before, but all the things that happen in our classical world. So this is classical 2-meter scale world. So our classical 2-meter scale world, the velocities or speeds must be less than 10% of the speed of light. That means that they have to be less than, so the speed of light is roughly 3 times 10 to the 8 meters per second. So if you divide that, 10% of that would be 1/10 of that. So the fastest we can go is 3 times 10 to the 7 meters per second. Before we have to disregard classical physics and include relativity. So this is as fast as we can go. Right here. We can go this fast. All right. The other thing I said is that we can use microscopes, optical microscopes. So if you can see microscope, I lost my C scope. So if you can see the object, here's our object, and you can see it within a microscope, optical microscope, then it's an object that we can look at and use in the classical physics world. Okay, so here's our object. All right, and then of course our force of gravity, or another way to put it is gravity is the only field that we'll be working with. Okay, so we're working with the gravitational field, I'm telling gravitational field. All right, the reason I'm throwing in gravitational field right now is because next semester, and you're probably going to take the next semester, you're going to look at fields, electromagnetic fields, and you're going to start looking at things in terms of fields. And even though we don't typically start out looking at gravity as a field, it is definitely a gravitational field, and there are comparisons. Okay, so when we get to Newton's universal law of gravity, we'll be talking about it in terms of it as a field. I just may not be mentioning the fact that it is a field. Okay, a gravitational field. So, okay, so let's keep going. Like I said, this is all the classical physics world, okay, classical. And we don't want to talk any further past that point. So we're just going to leave it there. That is the scope of our that's the edges and the limits of what we're going to be looking at. Okay, so models, theories, and laws. Well, I kind of talked about models, theories, and laws. To me, models, theories, and laws, these are all things that you hold in your brain that you feel are the way the world works. Okay, this is our mapping in our brain of nature or reality, or however you want to think about it. There are they're not going to have three different words and not have them mean something different, right? They're going to say, oh, a model is this, a theory is that. All right, I am not. Mostly all of these things are simply mapping our brain, in our brain, some nature. Okay, model, a theory, a law. To me, they're all the same thing. It depends on the time frame. So Newton, when he did his thing, they used laws. Okay, modern times, gravity, for instance, is a theory, right? Evolution, theory. All these things are theories because they continually get added to, tweaked a little bit here and there. For the most part, they don't change very much, right? But every once in a while, a little tweak here or a little tweak there happens, and maybe they get a better decimal point, one more decimal point to their significant figures on those things. So a theory would be a more modern way of looking at it, and actually the transition happens in the 1800s. So next semester you'll watch how they go from laws to theories. All of these things are definitely models, okay? But a model is a more initial thing. So initially, we have a model of the world. Okay, so I want to do what we're going to do in our first lab. Okay, so here's what we're going to have is a jack stand. Okay, and the jack stand does something like this. And there's a axis right down the middle with a turn screw thing that as you turn this dial one way or the other, it will raise or lower the jack stand because the threads on the screw cause these pieces right here to either get more narrow or get further apart. As they get more narrow, the jack stand raises, okay? And as they get further apart, then the jack stand lowers. So there can be a model. We would say, oh, initially we're going to look at this and we're going to say, oh, I want to create a model, which would be nothing but an equation that is a function of the number of turns, okay? So we're all taking calculus or have had calculus, and we understand then at that point that functions of a certain thing, so we'll put functions of the number of turns, which we could rewrite as f of n. Our function of the number of turns then would be something that is related to n. So when we do our experiment, we're going to say, oh, I want fn to be, I don't know, some constant, c plus, let's say we want to do a polynomial thing. So we'll have a constant times b to the n to the 1. And we could say a times n to the 2. We could go on, if we wanted, to get finer and finer with our polynomial, but let's just leave it at this. Let's just leave our polynomial like this, and we could say that this function is equal to the height of the jack stand. Okay, so what would you want to do at that point? Some people might say, oh, well, if it's going to be the height of the jack stand, instead of f of n, my function of n, I might want to say h of n, and then say that that's equal to, and some people write their constant first, some people would write a n squared plus b n plus c, like that, as their theory for the model, right? So this is our theory of how a jack stand might work, okay? And we will be doing this, so that's one option for a model that you might want to do. So what is that going to do? That is going to predict the behavior I always want to stick a U in behavior. I think in a past life I was British. Okay. Predict the behavior of a jack stand. Okay. And it's not just the behavior of the jack stand, but it's the behavior of the jack stand in relation to the number, not mumber, number of turns of the dial. So we'll be turning that dial complete integer turns, right? Where you can cut it in half. You can do all kinds of stuff. That's fine too. But a whole turn would be a whole turn, and then a half turn would be a half turn. At any rate, as the turns of the dial happen, we want to create some behavior for that. So we propose our model. this model is our quote-unquote theory, all right? And we're going to look at it through experimentation. If we go over and do it over and over and over, we might be able to refine our theory, refine the way that we're looking at it, and come up with a better model. So we might take this and it will iteratively get better through our theory and experiment, and what is the true or real way that this thing happens. We're going to be doing this back and forth until we can get closer to the truth of the matter. Okay? So, now, in the end, once you get to a certain point, repeated verification. So let's just do it the way they do it, how they talk about it. You have a model to start. You work on it a whole bunch. You get a theory. So model leads to a theory, and then eventually you get a law. But like I said, theories are the only thing we have. We don't have laws really much anymore. Chemistry might have laws, but again, that comes back to a time when laws were the epitome of it, of the peak, right? But laws aren't, I don't know. Conservation of energy is a law, and I follow that law just like you do. There's no way around it, but yeah, I don't know. Theory, everything changes because we never know the truth. So it has been kind of assumed or adapted that we use theories as the ultimate thing now, because laws just aren't the thing. Laws are they're not meant to be broken. I don't want to say that. Laws are often found still to be not perfect. They don't predict or describe behavior completely, and therefore theory, we have found, sorry about that, theory is pretty much as good as we get, right? Theory is as good as it gets. But anyway, classical physics has laws. Newton came up with things, they called them laws, and that's as good as it gets. Okay. So let's move on to our next thing. And how much time we got? All right, let's start in on it. Units and standards. So we've got physical quantities. Quantity, what does that mean? Physical quantity. Let's clean up that. Physical quantity. Quantity. That assumes numbers, right? You have to numerically say how much of it that you have. So how can you do these things? You can measure to get your number for the physical quantity. And we can only measure, believe it or not, we're only able to measure length, time, don't get me started on time, and mass. Okay? So these are the things that we can measure, and then we know some stuff, right? We measure it, we get a number. So we can come up with a number for the length, we can come up with a number for the time, and a number for the mass. Every single thing else is calculated. So what if we want to know the speed of something? Well, we've measured the length. So we take our length measurement and we divide it by our time measurement and we get our speed measurement. Okay, so that equals the length divided by time. So we've done two measurements and we can get our speed. Another one, we won't see this for a while, but momentum. And that is equal to our mass times our speed, right? Well, that's really just the mass times our length divided by time. So momentum, that's it. Let's do one more. We'll do force, which we will definitely get to. Our force is our mass times our length, and it's divided by time squared. Okay, so that is a force. So these things, speed, momentum, force, these are calculated. We can only measure these things here. Test question, by the way, for sure.
How's it going?
I am recording a video. Thank you. So, I just got a question about how's it going. And well, I'd like you guys to tell me how it's going. Hopefully, it's going really great for you. So, let's go to this next thing here and we'll talk about units. Let's talk about units. All right, length. Length. The units of length are meters. Mass. Units of mass are kilograms. Okay, keep that in mind. It's not grams, it's kilograms. Okay, so not grams. Time. We've kind of already talked about time and length a little bit, and I definitely used meters. And I used seconds. So we've got meters, kilograms, and seconds as our units. Now, okay, everybody goes, well, why these? I would rather use feet, or I would rather use, pounds or slugs or whatever it is. So for mass, this group of physicists and I don't even want to get started on how or why, but we needed to get together and make sure that everyone was on the same page with our units. So in France is where the group comes from. So that's why it's called Système Internationale, or the international system. Okay, but we call it SI, so you may as well call it Système Internationale. That way you'll have it in the correct order. And SI units are the thing that we use. Okay, so we're going to use that in this class, and the reason why is because it all kind of hangs together and makes things nice. So we can go back up here and look at our calculated things. And in terms of our international system, our units for speed are meters per second. Okay, our units for momentum would be, and I try to put units like this. So we'd have kilograms, meters, per second. And here our units for force it's our mass, so it's our kilogram, it's our meter, and it's divided by seconds squared. Okay, that happens to equal 1 Newton. Okay, because the folks that created this international system, they decided to honor Newton with these things, so then we can, it simplifies our lives and honors Newton all at the same time. So we use that. So a Newton is a unit of force. Okay, let's cut here, and well, okay, not quite yet. Let's just quickly do the metric system. A lot of people think that the metric system A lot of people think the metric system is the units, but the metric system doesn't handle the units, it handles the orders of magnitude. For those units. Okay, so we could have a kilogram, for instance. So we have a gram, 1 gram, or we could have 10 to the 3 grams, and that equals 1 kilogram. Okay, and that is the SI unit for mass. Okay, but we could have 1 meter, or we could have 10 to the 3 meters, and that's equal to 1 kilometer. Okay, again, all we've done is add the metric system to our SI system. Okay, and let's just go through orders of magnitude here real quick. 10 to the 9. These are things that I don't put on tests, so you might want to convert these to either memory, or if you're not going to commit it to memory, then put it on your cheat sheet. Okay, so so we've got 10 to the minus 9, which is nano, 10 to the minus 6, which is micro. That's the symbol. I'll put the symbol here. And micro. 10 to the minus 3 is milli. We're going to skip the 1 and go to 10 to the plus 3. 10 to the 0, I should say. And go to, that's kilo. K-I-L-O, Colorado Springs, Pueblo. And Denver sometimes, I think they say now. This is mega with a big M. And let's do giga with a big G. Okay, let's just give those out. Should we do one more? Okay, let's do one more. 10 to the 12 is a tera. And if you remember your bytes, right, it's easy to remember your terabytes versus gigabytes versus megabytes. And you know how old a person is depending on whether they had computers with kilobytes or megabytes or gigabytes. I'm this old. Okay, so tera. Okay, there are more, right? You can get smaller than nanos. 10 to the minus 15 is a femto. Something, whatever, femto blank. FM if you're going to do meters, right? So, yeah, Okay. That's it. Let's continue in the next video, and we'll get some more of this good physics stuff in.